So, welcome again to the course Fundamentals of Solar Photovoltaics and Technologies. So, in this lecture today we will continue our discussion on semiconductors. So, let us just briefly recap what we did in the last few classes. We looked at the origin of band gap and which happens because of diffraction of electron waves in the crystal at the boundaries of Brillouin zones, and as a result you create two energy states at those values which result in a gap. The band structure of different materials requires complex calculations which we have not gone through, but if you do carry out using the concepts of reciprocal lattice etc., then you figure out that band structures in materials are very different depending upon their nature. So, for example, in semiconductors, in metals the band structure show, so this is on the left the band structure is of aluminum, on the right we have that of copper, and these two show that the density of states is quite different in two different diagrams, but what we do not see is absence of a continuous gap across the K space in the energy. As a result, there is no gap in these materials, and these are metals. And somewhere in between we have a Fermi energy above which the energy levels are empty at 0 Kelvin. On the other hand, if you look at semiconductors, they show a different band structure. There is a presence of continuous gap in the energy across the K space. So, these are two examples, for example, for silicon and gallium arsenide, and we see a continuous gap across the K space in the energy, and in between this energy gap what we have is Fermi level. Fermi level lies right at the middle of the band gap at 0 Kelvin, and for a undoped semiconductor, which for a pure semiconductor, and depending upon whether the minima and maxima of conduction and valence band match or do not, they are defined as direct and indirect band gap semiconductors. So, for an indirect band gap semiconductor, the minima of valence band, conduction band and minima of conduction band and maxima of valence band do not coincide in K space. So, as a result, optical absorption will require a phononic transition from K1 to K2. This results in weaker optical absorption in indirect band gap semiconductors. In contrast, in direct band gap semiconductors, the minima and maxima, they are at the same K value. As a result, the optical absorption of these materials is much better. And because of curvature effects in these band diagrams, we see two entities. One is electron with the positive mass which is in the conduction band edge at the boundary of first Brillouin zone, and then we get a negative curvature effect which results in an electron with a negative mass which is construed as hole, which is the counterpart of electron in valence band, which is a positive charge. So, you can say electron with a negative mass, meaning hole as a positive charge with positive mass, and this happens at the valence band edge at the first Brillouin zone boundary. These two entities have different masses because of different curvatures. As a result, they are not often the same, and electrons are generally lighter. As a result, they tend to have higher mobilities as compared to hole. So, electron moves faster as compared to the hole. So, let us now look at some more examples of these materials. So, we of course have seen silicon, which shows an indirect band gap band gap. On the right we have germanium, which is again an indirect band gap semiconductor, wherein we have this minima is here and maxima is here, and you can again see that there is a need for a photonic as well as phononic process. In contrast, if you look at gallium arsenide, we have already looked at that. It is a direct band gap semiconductor with minima and maximas coinciding in K space. Something like indium phosphide also shows the maxima and minima coinciding. There are many other materials, for example, direct band gap semiconductors of relevance for us is cadmium telluride, gallium arsenide, of course, that we have seen on the left, but copper, indium, gallium selenide, even perovskite materials tend to be of direct band gap. So, many of these materials that we use commercially in different devices, they are all direct band gap semiconductors, hence they are better absorbers. The direct result of this is direct band gap semiconductor requires lower thickness. So, as a result, lower thickness for light absorption, and indirect band gap semiconductors, they require higher thickness to absorb the same amount of light. Okay. So, let us now look at how do we determine the band gap. Having known what band gap is, let us see how do we determine the band gap. Band gap is determined by two methods. First is the optical absorption method. So, for example, this figure shows the measurement. So, you shine light on the semiconducting material with respect to a reference, of course, and this is, for example, for pure indium antimonide, and you see that absorption coefficient is plotted here as a function of energy, and you see that the material starts absorbing only from this particular point and it increases up to higher energies. So, what it shows is that this is your band gap. So, it is at this point the energy starts getting absorbed. This point corresponds to the band gap of the material. There is another way to measure the, so you can also do extract this band gap by plotting the absorption coefficient. We will do that exercise later. How do you fit the data and extract the absorption coefficient? Second method to determine the band gap is temperature dependence of conductivity. So, if you plot the conductivity as a function of 1 over T or 1000 over T, it should show a Arrhenius like behavior. The plot of log of conductivity versus 1 over T should be a linear plot, and the slope of that is proportional to the band gap. So, so basically you can say sigma is equal to sigma naught into exponential of minus Eg by kT, and that should give you the conductivity. So, minus Eg by k will be the slope, and hence that will give you so these two methods, either temperature dependence of conductivity or optical measurements, they can give you the determination, they can give you the value of the band gap of the semiconducting materials. So, now let us see in the perspective of this band image, how do metals look, how do semiconductors look, and how do other materials look. So, for example, let us look at first the case of metals. So, let us say we first plot the core bands. The core band is 1s, and then we have second core band, which is, let us say, 2s, and between these, as we saw, there will be a band gap, and then we have similarly we have 2p, and then we can have 3s and 3p and so on and so forth. So, there will be 3s, there will be 3p, and 3s and 3p may be overlapping, or they may be separated from each other. That depends upon material to material, but this is where we start having materials like aluminum, sodium, magnesium. So, atomic number 11, 12, 13, all these materials, they start appearing here, and the band structure here in this section will depend upon the band structure. So, these bands which are totally filled at the bottom, these are called as core bands, and the bands which are partially filled here, they are called as valence bands, and these are, you can say, they are partially filled. So, you can say they are partially filled for metals. So, of course, for something like sodium, you can say sodium is 11. So, it says 1s2, 2s2, 2p6, and then we have 3s1. So, we have one state empty. So, you can say that there might be a gap between 3s and 3p, and so this could be a gap, and 3s will have only one here. So, it's a partially filled band. So, it will give you a partially filled band. In case of magnesium, if you look at, we have 1s2, 2s2, 2p6, and then we have 3s2. What happens in case of magnesium is we have, although we have 3s2 here, in this case what happens is that this 3s band overlaps with 3p band. So, there is no gap between the two, they do overlap, that is how. So, this is 3s2, this is 3p6. So, although this is filled, the electrons are able to migrate to 3p band to conduct. So, these are overlapping s and p bands. So, depending upon the material, metals basically what they have is they have continuous energy states available, either because of either within the same band or because of overlapping of bands. So, that is how metals tend to be more conducting as compared to semiconductors. At the bottom below the valence electrons, what we have is core bands which are totally filled, and they do not take part in conduction typically. So, let us now define metals versus semiconductors. So, let us say we first draw the diagram for metals. So, metals have one particular band. So, of course, there will be core band below. So, this is band, let us say core band, and then we have valence band. This is valence band, and here we plot energy. Okay. So, this is partially filled, we can say it is a partially filled, or you can have a situation like we can have a core band and we can have a filled band which is overlapped by a empty band. So, these are called as overlapping. So, this would be filled, this is empty, and again in the context of availability of energy state, it will be construed as a partially filled band. So, filled, so there is a overlap between the two. So, you can say this is sort of overlap. Okay. So, this is how metals are. If you look at semiconductors or insulators, So, in that case what happens is that at 0 Kelvin we will see a band on top which is totally empty, and then we have a band at the bottom which is totally filled. So, this is filled, this will be valence band, and this will be empty, this will be called as conduction band. And this gap will be Eg, which is typically below 2.5 eV for semiconductors. Okay. For insulators, it will be little different. For insulators, it will be empty band followed by a large gap. So, we have filled band here, this is again valence band, this is conduction band, empty, of course, it's at 0 Kelvin, and this gap is larger than 2.5 eV in case of a insulator. So, both insulators are often called as wide band gap semiconductors. So, they have similar band structures, it is just that the band gap magnitude is much higher in case of insulators than in case of semiconductors. So, that is how they look like in case of these materials. So, if you look at now in the context of resistivity and conductivities. So, if you plot, let us say, increasing order of conductivity Siemens per centimeter, on the left hand we will have something like metal whose resistivities, whose conductivities may vary from 10 to the power 8 to 10 to the power 4. Okay. And then somewhere in between we have germanium silicon like semiconductors, and this region will give you so something like germanium, silicon, here we can say copper, gold, silver, etc., iron. These materials will have conductivities ranging from 10 to the power 0 to 10 to the power -4. Okay. and then some on the far spectrum you start moving, you have insulators, glass to diamond to other materials like fused silica, polymers, etc. And these will have conductivities starting from 10 to the minus 8 to 10 to the minus 20 and even lower. So, this is how these materials will stack up. So, these will be higher Eg, these will be intermediate Eg, and these will be overlapping or partially empty bands. And that is why metals are conducting, because they have states available for them. Semiconductors are not conducting, insulators are not even, they are even more poorly conducting. So, basically this is what it means in the context of band structure. Because of presence of gap, you require thermal and electrical or optical energy that makes electron move from lower band to higher band. So, let us say if we look at it in the context of so we have, in case of metals, we have a filled band, then we have another band which is partially filled band, and then we have another band which is empty band. So, we can represent these. So, the y axis we have energy increasing. So, this is your filled band, this is your partially filled band, and this is your empty band. And this is your filled band, totally filled. So, when you apply stress, which could be electrical, let us say, then electron can move to these next energy levels without needing to overcome a gap. These are your gaps. Alternatively, you can have a situation, this band is partially empty, the next band could be like this. So, this could be an empty band with states like these. Let us say this is all filled, this is just hypothetical, I know in terms of numbers it may be little off, but although this is filled, it can always cross over. So, this can be, this is your case of overlapping bands. And this is the case, for example, in case of magnesium, and this is the case, for example, in case of sodium. Okay. So, that is why when you have these atoms in a material and you have the sea of electrons around it, you apply electric field and your current will start flowing in that direction. So, that will give rise to conduction of carriers, because they can easily conduct through the states that are available. The thing about metals is that their resistivity increases with defects. So, if you increase the grain boundary concentration, the resistivity goes up, dislocation content, impurity concentration, vacancies, all of these factors lead to increase in resistivity, and that is because these entities called defects, they lead to decrease in the relaxation time because of scattering. They cause scattering, and this scattering reduces the relaxation time. As a result, conductivity goes down, or in conductivity resistivity goes up. So, if you plot the so basically you can say all of these act as scatterers, carrier scatterers, and if you plot resistivity as a function of, let us say, temperature, resistivity is in ohm meter, and so in case of, let us say, pure copper, the range can be anywhere from 1 into 10 to the power 8 minus 8 ohm centimeter to this could be 6 into 10 to the minus 8 ohm meter. So, you can just make the division here. Okay. So, copper, if you look at pure copper, it will show something like this, but if you add some impurity to it, this would be copper plus impure copper, which means copper plus some x% of nickel. So, you can see that this has increased, the resistivity has increased at a given temperature. Similarly, if you deform it, so this is pure copper deformed, again the conductive resistivity has increased. And if you now take impure copper plus deformation, this can increase even further. So, both impurity concentrations, vacancies, so temperature of course increases. As temperature increases, the resistivity goes up because of increase in vacancy concentration, because of increased atomic vibrations. So, temperature of course will give rise to increased vacancies and vibrations, and they will give rise to decrease in relaxation time. And these things like impurities, deformations will cause dislocations, grain boundaries. If you make it fine grained, for example, if you increase the grain size, if you decrease the grain size, so this will be effect of lowering the grain size. So, that is how it works. Your materials, they show effect of thermal increase in the resistivity plus impurity related defect, increase in the resistivity plus a component related to defect. So, these three are summed here: thermal, impurity and defect, and these are summarized in this equation here. So, basically we can say the resistivity increases with temperature, increases with the impurity concentration, and increases with percentage cold work, or you can say percentage deformation. And basically we can say that the temperature dependence may be both related to defect, that is vacancy, plus vibration. So, this could be vacancy, which is a defect, plus vibrations, both the factors taken together. So, rho T is rho defect plus rho thermal, and if you plot it like as a function of temperature, the resistivity, initially you observe a defect related part, and then because of thermal vibrations. So, this is how the behavior is observed. So, this is because of defects and this is because of vibrations. That is how the. So, now what we have seen so far is that if you plot resistivity log of sigma as a function of temperature, what we see, for example, for tungsten, a metal like tungsten, it shows a decrease. This is tungsten. Its conductivity changes from something like what's the number, 6.5 to 6 to 7. It is, I think, ohm per meter inverse, and something like silicon will change like this. It will keep on increasing. So, forget about the numbers, but the point is, in case of metals, as you increase the temperature, the conductivity tends to decrease, but in case of silicon, which is a semiconductor, conductivity tends to increase. And why this happens is something that we will see in the next class. So, what we have done today, we have seen that first of all, how do metals and semiconductors, they look differently in the context of band structure. Metals have overlapping or partially filled bands, valence band, that is how conduction occurs without needing to overcome the gap. Semiconductors, on the other hand, at 0 Kelvin have a fully filled valence band separated by energy gap with respect to top conduction band, and for any electron to conduct, it will require to move into conduction band, which will require you to put in energy either in the form of thermal energy or electrical energy or in the form of optical energy. And metals show a different dependence on temperature. resistivity increases as a function of defect concentration, deformation and temperature increase. On the other hand, semiconductors show an increase in conductivity as a function of temperature. That we will see in the next class. Why does this happen? Thank you.